All right, well, good morning, everyone. Hope everyone had a very nice weekend. Today, or really this week, again, we're shifting gears in the overall class. So thus far, we've been talking about descriptive analyses primarily, and this week we're shifting to multivariable modeling. So kind of get your thinking hats on, because again, we're shifting gears a little bit to think more about models rather than individual descriptive analyses and some of the subtle points that come up when we're trying to fit regression models to complex sample survey data. So thank you for submitting homework number 3. As far as I can tell at last check, most people got those in on time without any issues. So again, Young Chan and I will work to get those back to you as soon as possible with comments and get the solutions posted as well. So homework assignment number 4 is officially posted today. So this 4th homework assignment is designed to give you practice with the methods of linear regression. Okay, so we're going to start our discussion with talking about regression models for continuous dependent variables. Some of you may be working with categorical dependent variables, and that's fine. A lot of the topics that we talk about today will apply in general to different kinds of regression models that you might be fitting, but we're starting with continuous dependent variables. And all of the parts of this particular homework exercise are designed to give you practice with linear regression in particular. Okay? Now, as with the other assignments, there is some kind of a progress monitor related to the final project. So at this point in the course, as you're working on this assignment and we get into the month of July, if you're going to be considering multivariable models in your project, you should at least be discussing with your team the dependent variable or variables and the predictors that you'll be using in your models. So you guys should be converging to the types of models that you want to fit to answer your research questions, assuming that you are going to be using multivariable models. Okay, so at this point, you should really be at that discussion stage and possibly fitting some preliminary models using the techniques that we're going to be discussing this week. Okay, so again, the whole week's dedicated to getting into regression modeling and linear regression. But at this point in the final project, you should be having those discussions and thinking about some initial models, especially after the lab on Friday. Okay. Again, you don't have to turn in any output or email anything related to this progress check with your final project, but just keeping the big picture in mind. That's roughly where you or your team should be at this point in terms of the final project. Okay. Okay, so let's look at the specific exercises then. These are multiple parts of ASDA exercise 7.2. Most important thing I want to emphasize, do not do parts A through C. If you're doing parts A through C, you're doing unnecessary work. Okay, it happens every year that somebody submits parts A through C, okay, and then they spend a lot of time submitting this homework. Don't do parts A through C. The assignment's only asking you to do D through H. Okay, so start with part D. All right, so with this problem in general, we're trying to fit a linear regression model to the European Social Survey Russia data. And again, you can find that data set up on Canvas. You've been using it for previous homework assignments. So you're looking at predictors of a dependent variable that measures satisfaction with the government. Okay. Those predictors are listed in the early parts of the problem, so take a look and see what they are. There's a political scale, there's gender, and there's self-rated health status. Okay. So part D is asking you to fit the preliminary model with the retained predictors from part C. I want you to just start with all of those predictors considered simultaneously in a model for satisfaction with the government. Okay. So you're given what those predictors are, start with all of them simultaneously. Don't do a bivariate analysis, just start with all of them simultaneously and look at their relationships with the dependent variable. Now, part D says, fully account for the complex sampling features. So we're going to talk about what that means in the context of regression modeling. But again, like we've been doing with the design-based analysis so far, use the weights and use the stratum and cluster codes to fit that model initially and perform variance estimation. Okay, so that's what we mean by fully accounting for the complex sampling features. I also want you to request design effects for the estimated coefficients in that model. Okay, so again, not something that's often reported with regression output, but just to drive home a couple of key points related to design effects, I want you to compute design effects for each of the coefficients being estimated. And if you have a categorical predictor, there could be multiple coefficients associated with that one categorical predictor. We'll talk about that today as well. Okay. Then, once you've fitted the model, produce a residual versus predicted values plot as part of model diagnostics, and a histogram with a superimposed normal curve of the residuals. So I want you to think about some basic model diagnostics for this initial linear regression model, some visual diagnostics. And then there's 5 sub-questions to part D. Do the residual plots that you've generated indicate acceptable model fit so far, with the model being considered? What other techniques might you use to assess model fit aside from what I've listed there in part D? So what are some other metrics or plots that you could make to look at model fit? What do the design effects indicate about the relationships of each predictor? So what are the design effects telling you about those relationships? How many degrees of freedom are used for the significance tests and how are they calculated in this context of regression modeling? And then what is the weighted R squared for this model and what exactly does that mean in plain English? Okay, so looking at some basic assessments of model fit with this preliminary model that considers all of the predictors simultaneously. Okay, so that's part D. Part E then says test the interaction of gender and the left-right political orientation, that 3-category variable, in the preliminary model. Okay, so part E says include the interaction between gender and your left-right political orientation. Okay, so then we're going to talk a little bit about interactions today, but you have to think about what hypothesis you're really testing when you include that interaction, right? You're testing the hypothesis that the relationship of that left-right political scale may vary depending on gender. Or in other words, you're testing gender as a potential moderator of the relationship of that left-right political scale. Okay, so that's what you're doing when you add that interaction to the model. Then we need to perform a design-adjusted wall test for that interaction that we've added. So we're going to talk about how to do tests of whether additional predictors are making a meaningful improvement in the fit of the model. So we're going to be performing that test for the interaction and then reporting the F-test, the degrees of freedom, and the p-value for the interaction. Is the interaction significant at the 0.05 level? And based on your answer to 2, should we keep that interaction in the final model? Meaning that there aren't main effects, if you will, of left-right political scale or gender, but rather their relationships with the dependent variable depend on each other. Okay, so that's the question that particular problem is asking you to address. We're going to spend a lot of time talking about interactions as we talk about regression models. This is something that people consistently struggle with, but they can really help you to answer some interesting research questions. Okay, so we're going to spend a lot of time on that. Okay, that's part E, is looking at that interaction. Part F is fit your final model based on whether or not you decide to include the interaction in that regression model, and prepare a table that's similar to table 7.5 in chapter 7 that shows the results, presents your estimated coefficients, presents the linearized standard errors, presents the information that would allow you to test significance of the individual parameters. Okay, and then include in that table variable labels, the estimated design effects. So you have to include the design effects with that table of regression results, and then any descriptive information in the columns that makes it easy to understand what you're presenting in that table. But again, you can look at table 7.5 to see what we're looking for. Okay, part G then says, fit your final model, but this time using the final survey weights and without the PSU and stratify variables for variance estimation. So part G is really getting at what happens if you were to fit the final regression model using the weights only, but you ignored the PSUs and stratification in the variance estimation. Would anything change about your inferences? Would anything change about your conclusions? And line up the standard errors based on those 2 approaches with each other so that you can see if there are any meaningful differences in the standard errors. Okay, so this is an exercise in seeing what happens if you naively ignore the sample design features when you're estimating the variances of the estimated coefficients. Okay, so this is giving you a chance to look at what might happen in that case. And then finally, part H says, write a brief paragraph. This is not pages. This is just a paragraph, like you would for writing up a technical paper or a research article or something like that. Explaining the methods that you use to estimate the model parameters and to estimate the standard errors. Okay. So it's not just the methods used that were to estimate the regression coefficients, it's also the methods that you use to estimate the standard errors. Okay. Making clear how you went about fitting that model. And as part of that paragraph, discuss how your conclusions might have changed if you had not performed that fully adjusted design-based analyses that incorporated the cluster sampling and the stratification. So going back to what you saw in part G, see if your results were sensitive and your inferences were sensitive to whether or not you accounted for the cluster sampling and the stratification. Okay, so that's again, just a paragraph, not two paragraphs, just one paragraph, saying what methods you use for estimation, what methods you use for variance estimation, and then talking about the impact of the cluster sampling and the stratification on your variances of the estimated coefficients in that final model. Okay, so we'll talk about linear regression all week, driving up to this point, but these are the parts of exercise 7.2 that you're going to be submitting for homework number 4. Okay, so questions, comments, thoughts about any of those parts of exercise 7.2? Questions, concerns, thoughts? You have Jupiter?
I think on part F,
yeah,
it says we should prepare a table result similar to table 7.5.
right.
So it means from part D, there's no need for anything like that.
No, part D is asking you to look at the residual diagnostics and answer those questions.
Yes.
Yeah. No, that part F is where you're actually showing the estimates. But the reason that you're not doing that until part F is because you have to make a decision about the interaction. Right? Your results in part F either may include or may not include the interaction, depending on whether your test found it to be significant. Okay. And 7.5 is on page 241. Okay. Other questions, comments about the homework number 4? Okay, so homework number 4 is due on Monday again. So you have the week to work on it. So again, kind of work on it in parallel with the material that we'll be discussing in lecture. Okay, now before we get into our discussion of linear regression, any general questions about the material covered last week or related to your final projects right now? Any general questions? I know I have a couple outstanding emails that I'm working on, but any other questions that I can answer more generally related to the final project or the work that you're doing? Very good. Okay, cool. Let's get into linear regression. Okay, so this is going to be a 2-part discussion. So today, part 1, we're going to be reviewing some of the basics of fitting linear regression model. Again, this may be a review for most of you, but we want to make sure that we have these fundamentals down in the case of simple random sampling. Because then in part 2 on Wednesday, we're going to discuss what changes when we're fitting linear regression models to data from complex samples. So given that solid conceptual understanding of the basics of linear regression for simple random samples, we're going to then see what gets modified, what gets adapted on Wednesday when we're dealing with data from complex samples and fitting regression models. Okay, so that'll be our 2-part discussion this week. Okay, so more generally, when we talk about regression analysis, regression is a study of the relationship between variables. Okay, I emphasize relationship. I do not anywhere near there say causal effects. We cannot use linear regression to demonstrate causal effects. Okay, there are other techniques to demonstrate cause-effect relationships between variables. Generally, regression is just used to study relationships between variables. Okay, and that's going to be our focus as we go through interpretation and so forth. We generally talk about 2 different types of variables in this context. We have response or dependent variables. Sometimes these are called left-hand side variables, depending on your field. And then you have predictor or independent variables, and these might be called right-hand side variables, covariates. explanatory variables, regressors, again, depending on your field. We're typically going to refer to predictors and or covariates when talking about these variables in this particular course. And I'll usually refer to dependent variables when talking about the so-called outcomes or left-hand side variables. It is important to keep these distinct because the way that we formulate a regression model, we're saying that the value of the dependent variable depends on the values of the predictor variables. In some of your prospectus descriptions, a couple of you were mixing up those terms. Okay, so it is important to keep these terms straight when clearly defining the regression model that you're interested in fitting. Okay, so the objective of fitting a regression model in general is to make inference about the expected value of the dependent variable or some other characteristic of the distribution of the dependent variable. It doesn't have to be the mean. Could be the 95th percentile or the median or something like that. We can use quantile regression. But we're going to start off talking about models for the mean, where we're making inference about the expected value of that dependent variable conditional on the values of the predictor variables. So if we condition on having particular values on the predictor variables of interest, what does the mean of the dependent variable look like? That's our objective when fitting these models. And the predictors are assumed to be known or fixed constants that are measured without error. Okay, so that's another key assumption here, is that we have nicely measured predictor variables without any kind of error, and we're modeling the relationships of those with the dependent variable. Now we're going to start off talking about linear models, where this is a class of models that's used to look at a relationship where the outcome is a linear function of unknown regression parameters. Okay, well, I'll show you what this looks like in terms of equations in a second, but the dependent variable is a linear function or linear combination of unknown regression parameters and the predictor variable. So that's what we mean when we talk about a linear model. And notation-wise, I'm going to be using y as the response variable and x referring to the predictor variables, usually a vector of predictor variables. And I'll show you the vector notation that we'll be using. So again, in the context of your final project, this week you should be talking with your team about what's our y and what are our x's and what do some initial models look like relating those x's to that y variable. It's about where you should be on your final project. Okay, so again, generally speaking, we're going to talk more about the specifics of linear regression, but generally speaking, the steps in fitting any kind of regression model, you always start first with postulating a model. Okay, this is kind of like when we talked about preparing for complex sample survey data analysis, the importance of reading the documentation first, thinking about your research objectives, all of that kind of postulation of what you think the model is or what you think the model should be should always come first. Always start with the scientific objective and the scientific question and the model that you think makes sense from a scientific perspective. Okay, you want to avoid so-called fishing expeditions, where you just think that you have a whole set of predictors and you want to toss them into an algorithm and see what happens. Okay, it's always best to stick to the science and say that I think this is the model that will make the most sense for the subject matter that I'm dealing with. Okay, so that model that you're postulating defines the general behavior of the response variable, again, given a set of values on the predictors, and it's based on your subject matter knowledge and potentially initial empirical investigation of the data, usually a healthy blend of those two. The model is going to have a certain number of unknown quantities called parameters that define the conditional distribution of that dependent variable. So these are your regression coefficients, but also in some cases, the variances of your residuals. We're going to talk about that as well in the overall model specification. Not every person in your data set, not every unit in your data set is going to follow the exact pattern as specified by the model. And so many regression models will have errors or residual terms that are simple devices that account for the failure of that model to provide an exact fit to the data set, where you can predict what everybody's dependent variable is going to be perfectly. That's not the case because there's random variation in the real world, okay? And those errors are a statistical device to account for the fact that the model does not fit the observed data perfectly. And we make assumptions about the distributions of those errors when fitting this kind of regression model. But we always start in step one with thinking about what the model should look like from a scientific perspective. And again, that's where you guys should be at this week when thinking about your final course projects, okay? Once you've postulated a model and you think you've specified a model correctly for the variables that you're working with, then you analyze the data, obtain estimates of those regression parameters and their standard errors, okay, depending on what you know about the source of the data. And that's what we're going to be talking about this week. Then you look at model diagnostics to examine the suitability of the model. And this, unfortunately, is the step that many analysts just ignore or forget about. You fit a regression model and you assume that everything that shows up in your output is what you should be reporting without thinking carefully about the assumptions that underlie that model. So another key thing that we're going to talk a lot about, in addition to thinking about interaction terms, is model diagnostics. This is absolutely crucial. And if you're often fitting regression models as a part of your daily job, you should be in that regular habit of assessing model diagnostics every time that you fit a model. And that's something that we're going to reinforce over and over in this particular course, is making sure to look carefully at model diagnostics. Depending on what you see in the model diagnostics, that may lead you to modify the model structure. And then you might cycle back to steps 1 and 2. Maybe you forgot something or you misspecified something in step 1. You refit the model, you re-examine the results, look at the diagnostics again, see if anything looks better, okay? So oftentimes it's an iterative procedure between steps 1, 2, and 3, okay? Then when you think you've included all the relevant predictors, the model diagnostics looks good, the model seems to fit the data well, then you can use the estimated parameters and their standard errors to make inference about the conditional distribution of y given x, but only when you've been careful about steps 1 through 3. That's the key point here. And again, this is not just for linear regression. The 4 steps in here are good practice for any kind of regression model that you might be fitting, okay? So that's the general process that we're going to follow as we go through our different exercises and examples. So as I mentioned in the first slide, our focus is going to be on a broad class of models called linear models. Again, these models are linear functions of these unknown regression parameters. So a very simple example of a linear model with a single predictor is that first regression equation that you see here on slide 5, where we say that the dependent variable y is a linear combination of the parameter beta 0, the parameter beta 1, the predictor variable x, and then again, this statistical device called the error that captures the fact that the model does not fit that data perfectly. Not everybody lies on that straight line relationship between x and y. So that error term allows for random variation around what's expected based on the fitted regression model, the expected straight line, okay? But that's a linear model that defines a linear relationship between x and y. We can also write down a linear model that defines a non-linear relationship between x and y. So it's important to keep that straight, okay? That second equation is still a linear model. The dependent variable is a linear combination of regression parameters and values on the predictors. It's still a linear model. It just happens to be a linear model that defines a nonlinear relationship between x and y. Why? Because we're including x squared as a predictor. So that defines a parabolic relationship or a curvilinear relationship between x and y, okay? But it's still a linear model. That's what's important to keep clear here, okay? We're often going to use vector notation just to make it easier to write down these models as we talk about different types of regression models. So we use that little tilde underneath the x or underneath the b to refer to a vector of either regression parameters or predictors. So thinking about matrix algebra, multiplying those vectors by each other results in that linear combination. Okay, but we'll often use that as shorthand just to summarize that, that linear model and that linear combination of parameters and predictors. Now, in contrast, notice the difference between this example nonlinear model and the linear models above. In the nonlinear model below, where these kinds of models can often come up in physical sciences, understanding relationships between physical elements, notice that there's a regression parameter that enters in the power of x, the way that that model is being defined. The dependent variable is therefore not a linear combination of the regression parameters and the predictors, because one of those regression parameters enters the model in a nonlinear fashion. Okay? So that's what distinguishes the linear models above from the nonlinear models below. And our primary focus is going to be on linear models for particular dependent variables. The beta 0, the beta 1, and the beta 2 parameters in these equations that I've set up so far, those are the regression parameters, sometimes called coefficients, that we're interested in estimating as a part of fitting these kinds of models. So that's really the objective of our analysis. Those are unknown fixed constant parameters, and we're trying to estimate the values of those parameters for the finite population that we're interested in. Okay, today, we're just talking about reviewing linear regression in the basics outside of that finite population framework. Wednesday, we're going to talk about what changes when we're dealing with finite populations, but that's really our overall objective, is to estimate those parameters that describe that conditional relationship of the x's with the y's. So that's going to be our focus. Okay, so here's the simple linear regression model for a given subject I. Again, we're using that vector notation, looking at a vector of predictor variables and then a vector of regression parameters denoted here by beta. Okay, so in that simple linear regression model, those epsilon sub I terms, again, are residuals for subject I. That's that leftover random statistical variation around what's expected, about what's expected based on the regression model. Okay? And we make assumptions about the distribution of those residual terms. Okay, so that's what distinguishes between different types of models. Okay, so starting with the simple linear regression model, one of the assumptions is that the expected value of those residuals conditional on the predictors. So given values on each of the predictor variables, the mean of those residuals is going to be 0. So it doesn't matter what set of predictor values you choose. Everyone with that same set of values on the predictors, on average, the value of that residual is going to be 0. So on average, a person looks like you would expect, given the regression parameters. Okay? So there's no error there on average. Another assumption that we make in the simple linear regression model is that the variance of those residuals conditional on the vector of predictor variables is equal to sigma squared, or a constant. We're going to use sigma squared to refer to that constant error variance that defines a model of interest. But that's an assumption, is that that error variance does not change depending on the values of the predictor variables. Okay, we assume constant variance no matter the values of the predictor variables that we choose. Okay. Yet another assumption is that the covariance of any two errors for different subjects in the data set, conditional again on the values of their predictor variables, that covariance of those two errors is 0. Okay. So different residuals for different subjects have no correlation. They're completely independent in the context of this larger overall model. So just thinking ahead to Wednesday, why might that break down in the context of analyzing data from a complex sample? Why might that assumption break in the context of a complex sample, given what we've learned about the nature of complex designs and design effects and so forth? Why might that assumption not hold?
Perhaps because within clusters, some correlation.
Right, within clusters, people could be correlated, right? So even after you've accounted for all the common predictor variables and the regression parameters, if two people have very similar values on Y, they may have errors that are going in the same direction, given the regression function. And in general, those errors from people that are coming from the same sampling cluster may very well be correlated with each other, just like we talked about with rho. So yes, Jupiter, you're thinking about it the right way for sure. Okay. So in complex samples, we need to think about how we should approach the modeling differently, given that this assumption here probably no longer holds, okay, given the nature of the sample design. Okay, what can we do differently, given that it's unlikely that any pair of errors are going to be completely independent? All right, so that's just kind of foreshadowing to Wednesday. And then finally, in the case of simple linear regression for a continuous dependent variable, we assume that those residuals conditional on the predictive variables X follow a normal distribution with mean 0 and variance sigma squared. Many of our significance tests that we'll be talking about for linear regression rely on this assumption of normally distributed residuals. Okay, so that's an example of something that we look carefully for when performing model diagnostics for a continuous dependent variable, that the residuals conditional on the values of the predictor follow a normal distribution. Okay, this is another crucial misunderstanding among people fitting linear regression models. Okay, suppose I give you, okay, a distribution of a dependent variable that looks like this. Okay. Is that a reasonable distribution of a dependent variable to consider for a simple linear regression model? Why not? It looks like it is 4 modes. So it's a multimodal distribution. But am I making any kind of distributional assumption about y? Have I said anything about y on this slide? Nope. As long as those residuals follow a normal distribution, I have no problem fitting this kind of distribution. Okay. What could be happening is that I have 4 groups in the data, A, B, C, and D, where if I include group as a predictor in the model, and then look at the distribution of the residuals conditional on having group as a predictor, if I was to look at the distribution of those residuals based on that kind of model, this is what I would see. Okay. So you could throw at me any distribution on a continuous variable. I don't care how it looks. As long as you include the right predictors in that model and those residuals conditional on the values of those predictors, follow normal distribution, I'm perfectly happy. Okay? This is another very common misconception. If somebody looks at a plot like that, they say, oh man, I can't use linear regression. I got to do something else. That's not the case. Okay, and that requires understanding, again, really what these assumptions are getting at. We are making a statistical assumption about the distribution of those conditional residuals. That's what defines this particular model. Okay, so important to keep that in mind, again, as you're starting to look at your data, thinking about the distribution, thinking about the relevant predictors, and so forth. And again, that's where roughly you want to be at in terms of your final projects right now. Okay. Now, keep these assumptions in mind moving forward, okay, because we're going to keep building the model up based on these assumptions. What are the implications of those assumptions? Well, first of all, the expected value of the dependent variable y conditional on the predictive variables x. Notice I'm always saying that. That's what's key to remember in regression. We're always conditioning on a given selected set of the predictors. That's the same as the expected value of that linear combination of the x's and the betas, plus the expected value of the residuals. And the x's and the betas are both constants. So the expected value of the x's and the betas is just the x's and the betas. Okay? Plus the expected value of the residuals, which is just 0. That's one of the assumptions that we just laid out on the previous slide. So the expected value of y conditional on x is this linear combination of the predictive variables and the regression parameters. We refer to that as the regression function. Okay? That linear combination is the regression function that defines the expected value of y when we condition on the predictive variables x. And again, we can just write that as this linear combination of the observed values of the predictors times their corresponding regression parameters. And usually we include an implicit predictor that's equal to 1 for everybody, corresponding to the intercept term. in the regression model. Okay, so that most regression models are going to include that intercept term, but some do not. Some omit that additional parameter there, which is fine depending on, again, the subject matter. So that vector of predictors is listed as 1, and then all the values of the predictors. We're going to assume in this class that there are P predictors of interest in a given regression model. Okay, so that subscript P is corresponding to the total number of predictors that you're interested in including in the model. And then we have, if you look at the transpose of that vector of regression parameters, that's all those fixed regression parameters that we're trying to estimate, beta 0, beta 1, et cetera, all the way up through beta P. Okay? Now, that's the mean of the dependent variable given values on the predictors. The variance of the dependent variable given values on the predictors is equal to sigma squared. Okay, so when we condition, same idea. If we take the variance of that linear regression model, the variance of that constant is a 0, and then we're left with the variance of those residual terms, and that variance is sigma squared. Okay, so that gives us the conditional variance of the dependent variable. Okay. Then, same idea, conditioning on the values of any two sets of predictor variables, the covariance of any two values on the dependent variable in the data set is equal to 0. And again, that's where, in the context of complex samples, that kind of part of this model specification breaks. We can't assume that any two values, even after conditioning on the predictors, coming from a similar sampling cluster, are completely independent of each other. Okay, so we need to figure out how to modify our model to allow for that. Okay, so building all this up, we would say that marginally, okay, so that is marginally across all the values of those predictor variables, the dependent variable y follows a normal distribution with a mean defined by that linear combination of the x's and the betas, that's the expected value, and a variance defined by sigma squared. And any two observations on that dependent variable are independent of each other. So we don't have to worry about any kind of intra-cluster correlation or anything like that when defining the distribution of the dependent variable. But all of those assumptions imply this marginal distribution. Okay? So the assumptions that we really need to check involve the residuals. If we were to change the assumed distribution for the residuals, we would have a different implied distributions for y. Okay? This distribution depends on the assumptions that we're making. This is not the default distribution of a given dependent variable. That's why it doesn't matter what the distribution looks like. We care about what the conditional distribution of the residuals are. Okay? So this is what's implied by making those assumptions. Okay, now, big thing, again, that we're going to stress as we go through different examples and exercises is interpretation. Okay? The software nowadays makes it incredibly simple to fit very complicated regression models, generate a lot of different estimated coefficients, lots of different estimates. Doesn't mean anything if you butcher the interpretation of the coefficients. Okay, so every time that we go through these examples, generating some estimates, looking at the regression coefficients, we want to be very careful about how to interpret the estimates in that particular model. So we're going to spend a lot of time talking about this as well. So let's take the case of the simple linear regression model just with a single predictor. Okay, and what you see here are two regression functions evaluated at different possible values on that one predictor variable of interest. Okay, so first of all, let's assume that that predictor variable x is equal to x naught, okay, some arbitrary value of x. Then the regression function says that the expected value of y is beta 0 plus beta 1 times whatever that value of x naught is. Okay, that's the expected value of the dependent variable, conditional on that value of the predictor. Okay, now let's suppose that we add 1 to that value of x naught. Okay, that's that second regression function. If we add 1 to that value of x naught, now the regression function says that the mean of y is beta 0 plus beta 1 times x naught plus the additional beta 1 because we had increased the value of x by 1 unit. Okay? So looking at the difference in the expected values of y given those two regression functions, we can say that on average, the expected change in y for a 1 unit change in x is simply equal to beta 1. If we take the larger regression function, subtract the smaller regression function, all that's left is beta 1. Okay, so that's the common regression interpretation of these coefficients, is that as that predictor increases by 1 unit, the expected value of the dependent variable is expected to change by beta 1, okay, whatever that parameter is. Now, more often than not, we're not fitting simple linear regression models with a single predictor. We're adding multiple predictors to that model. There might be confounders we may wish to adjust for the values of other predictors when focusing on the interpretation of one particular relationship. So let's suppose that we add a confounding variable z to the regression model that we were just considering. So again, two regression functions here, one with x equal to x naught, the other with z set to z naught, okay, some arbitrary value. That defines the regression function that you see there, where alpha 1 and alpha 2 are the regression parameters for x and z respectively. Now, if we look at the second regression function and we increase x by 1 unit, now we have that additional alpha 1 term in the regression function, but we still have alpha 2 times z naught. Again, if we go through the exercise of subtracting the smaller regression function from the larger one, what we're left with is alpha 1. The key thing to notice is that we kept that confounding variable z held to a constant value when making this interpretation. So we would say that alpha 1 is the expected difference in y that's associated with a 1 unit change in x with that other confounding variable z held constant. Okay? So in a given investigation, you have to ask yourself, as a subject matter knowledge expert, does it make sense for z to remain fixed while the value of x changes by 1 unit, by 2 units, whatever the case may be? Okay? This is the idea that predictor variables may be correlated with each other. And that assumption, again, in making this interpretation may not hold. We're going to come back to this when thinking about an issue called multicollinearity when fitting regression models. Okay? We're making this a certain interpretation, assuming that these predictor variables x and z are essentially orthogonal to each other, okay? Which means they're uncorrelated. It's possible to think about one staying constant while the other is changing. That's kind of implicit in this kind of interpretation here. So we always have to ask that question. Yep, George?
Yes, so I want to understand this confounding variable.
Yep.
When you indicated that this type of analysis is not a cause and effect.
Right.
But this variable that may exist, that may be affecting the relationship.
Right.
And I just want to understand when you are saying that it's not, if you are trying to measure the cause and effect of something,
Right.
Is a tool.
No, yeah, this is just saying when we adjust for that additional confounding variable, what is the relationship of the other variable with the dependent variable? All we're saying is that if you condition on, say, let's say z is like males and females, okay, and you fix z to be female. All this is saying is when you look at females exclusively, what's the relationship of this other variable x with the dependent variable? It's not saying anything about causality. It's just saying when you hold constant the values on other predictors, now what does the relationship look like? You're no longer marginalizing across males and females. You're saying when I look at females specifically, what does this relationship look like? Okay, so it's not causality. We're still just modeling a relationship. So even in this case, we don't want to say that we're estimating a causal relationship of x with y, conditioning on z. That's incorrect. Okay? This is just a relationship.
Because the other thing I was thinking about, maybe let's say, for example, the likelihood of developing hypertension, for example, and then maybe you have exercise status, maybe.
Sure.
Because I would think maybe somebody that exercises regularly, might play a role in whether that person.
Sure.
So I was not thinking of it from that. It's not that.
No, yeah, you're taking into account variables that could easily explain variability in the dependent variable. That's perfectly fine. And that's what you want to think about when postulating these models. But the causal issue says, okay, fine, flip x and y. You're still going to see the same relationship, right? These are just labels. What's the dependent variable? What's the independent variable? Causality says, as this goes up, this goes up. And the same thing would not hold if you flipped it around, right? That's what we have to be careful about. I mean, there's an entire class of methods for causal effects. These are not those. That's the key thing to recognize. Okay. So we're going to talk about anytime we make an interpretation in a multivariable regression model where you have several different predictors, okay? And we focus on one particular coefficient. We're going to say, what's happening when we hold all of these other predictor variables fixed as one given predictor goes up by 1? And we always have to have that question in the back of our mind. Does it make sense to make a statement like that, given what we know about these predictors? To say that all these other things can remain fixed while this predictor goes up. Okay? Well, we're going to keep coming back to that. Now, another key thing about interpretation is intercept terms. Okay? The intercept, remember, is the expected value of the dependent variable when all the predictors are equal to 0. Okay? All the dummy variables, all the continuous predictors, everything in the model is fixed to 0. Okay? So if we have variables in the model like age and income, height and weight, okay, does it make sense to talk about the mean of y when all of those different variables are equal to 0? Okay? Usually not. Okay? And that's because you're not going to find somebody in the data with a weight of 0 or an age of 0. Or if we're using the survey weight as a predictor in a regression model, someone with a survey weight of 0 doesn't exist, right? So usually the intercept as defined represents an expectation and a parameter that we're estimating, because we're estimating beta 0. It represents an expectation that's outside the range of the observed data, something that doesn't necessarily have meaning, okay? So reformulating the intercept in some way can help to make it more interpretable. And one very common technique is called creating a center set. We're centering the values on the continuous predictors. So suppose that X and Z in the model that we were just talking about are both continuous in nature. Okay? We could center those variables by subtracting the mean of each of those variables from the variable itself and creating a new variable in the data set that represents that centered value on the predictor. Now, when I have these new centered variables as predictors, having a value of 0 on the predictor means something, because a value of 0 means that X or Z are equal to the mean, either for the overall sample or for the overall population, depending on what choice we use for that mean. Okay? Now, the intercept can be interpreted, because I'm saying for people who have their values on X and Z set to the mean, for the average person, in terms of these predictors, what is the expected value of the dependent variable? Now it makes sense, okay, to talk about that intercept. So when you center like this, that will change the value of the intercept. But now it changes it to something more meaningful. A lot of times we can think of that centered intercept as the overall mean of the dependent variable. So on average, for all the people who are set to averages on X and Z, what is the estimated mean of the dependent variable? So centering is a very useful practice to make sure that all the regression parameters have a meaningful interpretation when you're trying to write down estimates and interpretation. So if you make the choice to take the intercept out of a simple linear regression model, you're forcing the regression model through y equals 0 when X and the other predictors are equal to 0. So again, that might make sense in the context of some applications, that when all these other predictors are equal to 0, the dependent variable can also be equal to 0. But you have to verify that that really does make sense, because removing the intercept changes a lot about how you interpret that regression model, because you force that intercept to go through that 0 point. Okay? So we'll keep coming back to centering as we think about interpretation. This becomes especially important for multi-level modeling. We're not going to get to that until the end of the class, but for those of you who are fitting multi-level models to continuous dependent variables especially, centering becomes absolutely crucial for estimating variability in intercepts. Okay, we're gonna come back to that later in the class. Okay. Okay, interactions in nonlinear terms. That's another very important part of thinking about the specification of regression models. So we definitely have to use caution when interpreting linear models that include these regression parameters that define nonlinear relationships, like we talked about earlier. So when beta 1 and beta 2 are both associated with the values on a predicted variable x, they're linked to each other. Okay? So depending on the value of x, again, y could change in a different manner depending on beta 1 and beta 2. So beta 1 by itself doesn't really have a meaningful interpretation because the relationship of x with y depends not only on beta 1, but on beta 2, okay, the nonlinear part of this. So beta 2 measures the extent of the nonlinearity in that relationship. So if we can simplify the model by taking out beta 2, if there's no evidence of a nonlinear relationship, we certainly want to do so because having beta 2 in the model complicates the interpretation of these terms. We wouldn't want to interpret beta 1 in the same way that we were just talking about, right? A 1 unit increase means this. We have to talk about what the value of beta of what x squared is when making that interpretation. They're linked to each other, okay? So we always start with those higher order terms if we're trying to define this nonlinear relationship and see if there's evidence in support of including that higher order term in the regression model. If there's not, then we can certainly simplify. But if there is, we're capturing an important part of that relationship and we have to make our interpretation accordingly. Okay? And the same thing applies for interaction terms. Okay, again, we're going to spend a lot of time talking about interactions because it's really important that we get these right. Okay, because they can reveal some very interesting things about these relationships. So another very, very common mistake that people make when looking at models that include interactions is to call beta 1 the main effect of x. It's not. Okay? There is no main effect of x or main effect of z in this model. Why? Because think about the interpretation of beta 1 in this context. Okay? Beta 1 is the relationship of x with the dependent variable when z is equal to 0. If z is not equal to 0, the relationship of x with y depends on beta 1 and gamma 1 in this equation. Everybody see that? All it takes is any non-zero value of z, and the relationship of x with y depends on that value of z. Okay? So I can't talk about an overall relationship of x with y. The relationship of x with y depends on my choice of z. And beta 1 is only the conditional relationship of x with y when z is exactly equal to 0. And that is not a main effect. Okay? That is an error that we absolutely want to avoid when you're interpreting regression models that include these kinds of interaction terms. Okay? So you think about the way that this model looks, that gamma 1 term tells us how that relationship of x with y changes when z goes up by 1 unit. Okay? So another very important thing to recognize about these kinds of interaction terms is that that regression coefficient should not be interpreted as some kind of overall effect, but this is a change in the relationship of one of those variables with the dependent variable as the other one changes in value. Okay, so anytime that we're talking about a regression coefficient for an interaction term, we're talking about a change in the relationship. We're not talking about an overall relationship. We're talking about how some relationship of interest changes. Okay. So I'm going to keep driving that point home as we're looking at these different kinds of models. The minute you look at an estimated coefficient for an interaction, the first word that should enter your head is change. Okay? It's a change in a relationship. It's not an overall relationship. And this has implications for how we interpret all different kinds of regression models. As we talk about how like logistic, Poisson, et cetera, depending on how we're modeling the dependent variable, always want to look at an interaction coefficient as a measure of change in a relationship.
Can I have an example about this? Because I am
Yeah.
a practical example.
Yeah, sure. So let's suppose in this case that Z is equal to an indicator variable for being male or female. Okay. So if I were to plot that relationship, say between X and Y for different levels of Z, okay, suppose that this, so again, going back to what I was just saying, beta 1, let's say that Z is 1 for females and 0 for males. And we want to see if the relationship of X with Y is moderated by gender. Okay? Does that relationship of X with Y change depending on gender? Right? So the relationship of beta 1 itself is the relationship of X with Y for males only. It's not a main effect. It's the relationship of X with Y for males only. So maybe that's this regression line here. Okay. So that regression line there is defined by Y equals beta 0 plus beta 1 times X. Oops. Okay. Why did I cancel everything else out? Because Z is equal to 0. The regression function is just defined by beta 0 and beta 1 times X when Z is equal to 0. Okay, that expected value of Y when Z is equal to 0. Now, suppose I'm a female. Okay, now Z is equal to 1. So for females, this might look like the regression line. We have to think about what the regression function looks like for females. Sorry, it's not a straight line, but trying my best here. So now that Z is equal to 1, the regression line is defined by an intercept that is beta 0 plus beta 2. Right? Now, Z is equal to 1. So now the regression coefficient, the regression line, the regression function for females has a different intercept. That gap in intercepts between males and females is beta 2. So beta 2 is the change in the intercept between males and females. Everybody with me so far? Okay. Plus, now the new slope for females is beta 1, which was the slope for males, plus gamma 1. It's a bad gamma, sorry, it looks more like an alpha. So I'm just making the point. Times X. Okay? So there are two change parameters here. Beta 2 is the change in the intercept for females relative to males. That's one change. Gamma 1 is the change in the slope for females relative to males. So if gamma 1 is non-zero, that tells me, in answer to my research question, the regression relationship between X and Y is different for females compared to males, which was the question that I set out to answer initially. So this is why whenever I read a paper or something that interprets beta 1 in this context as being a main effect, I get a headache. I don't like getting headaches. So if I'm refereeing that paper, it's probably going back. Okay? Because it's just an incorrect interpretation. When you're really breaking down interactions like this, it's important to get back to nuts and bolts and literally write down the equations like I just did to see exactly what role those coefficients are playing. Okay? And we can't talk about the relationship of X with Y until we know what the value of Z is in this case. All right? Everybody with me? So we'll keep driving this home when we talk about interpreting interactions in the context of linear, logistic, Poisson, it doesn't matter. Any regression model. When you see a coefficient for an interaction term, change. It's the very first thing you should think about. Not effect, change. Okay. Questions about this? Okay. Yeah, so then, like I showed on this previous slide, we had males and females. You could have 3 groups, right? You're going to have 2 coefficients in the model that represent changes in the intercept, right? If I have a categorical predictor with 3 variable or with 3 levels, I'm going to have 2 dummy variables in the model. We're going to come back to that in a second. So I'll have 2 change coefficients for the intercept. And then I'm going to have 2 change coefficients for the slope, right? I'm going to have an alpha or a gamma 1 in this case and a gamma 2. And that gamma 2 is just going to be how the x slope changes for the second dummy variable. And I have to pick a reference category. So you can extend this, you can generalize it to any kind of regression model you're talking about. You just have to sit down and write everything out as the model becomes more complicated. I have to do that every time. If somebody just plops down a regression model on the desk and says, how do I make sense of this? I got to write down these equations. Doesn't matter if you've been a statistician for 2 years or 50 years. You got to go through that same practice. Otherwise, you run the risk of making a mistake in your interpretation. Always got to write down the equations. Okay, other questions about this, about interactions? This is not the end of our conversation about interactions, but it's important to get this concept down. Okay. Before we get into categorical variables, I think that's a good time for a break. So why don't we break until about 10 after? And I'll come back talking about indicator variables, and then we'll spend a lot of time talking about diagnostics. Okay, once you fit a model, looking at diagnostics carefully. We'll go through some examples. Okay. Okay, so let's break till about 10 after, and I'll start back up. Okay, thank you.
Everything. Just changing the reference.
We should go back again. You're really good with it. You're really good. But she doesn't know how to stop. So yeah, she goes very fast, but like she doesn't know how to break. Yeah. Oh, she's so cute. Somebody is so fast. With ice cream. Just like I went also. Oh, yeah. Did you like it? Yeah. Fun. I liked it because I saw her fall down. Yeah. Nice. Yeah. But she's really fast. She's really good. So. Oh.
please. I hope there's only like someone, yeah. I showed the pictures of. Oh, these pictures are sweet. Your friend was so funny. You look like.
Okay, I think we're gonna start back up here. All right, so we briefly talked about what it means if you had more than two groups. I gave the example with males and females on the previous slide, but in general, when you have a categorical predictor variable in regression models, you're going to be including multiple terms associated with the categories of that predictor. And that's what we're going to talk about next year. So one way that you can account for the relationship of a categorical variable with a dependent variable is to include these indicator variables, or another, put differently, dummy variables, as they're sometimes called. And these are required to represent the effects or the changes in the mean in this context of levels of categorical variables in regression models. And there's many different ways to specify these dummy variables depending on how you are interpreted, or which has implications for how you interpret your coefficients. So we're going to focus on the approach to accounting for categorical variable changes and means using a 1-0 parameterization, or this indicator variable or dummy variable parameterization of these categorical predictors. Just really for ease of interpretation, but I want to make it clear this is not the only way to handle relationships of categorical variables with a dependent variable. So suppose, for example, you had a predictor variable X that was defined by race, ethnicity, and you had three categories: white, black, or other. Okay, just very simple case. When working with this kind of indicator variable technique, you have to choose a reference category of that particular categorical predictor. So one of those three categories has to become a reference category. We most certainly do not want to simply include X as a predictor in the regression model. Again, because as I joked about a couple classes ago, a 1-unit change in race means absolutely nothing, unless you talk to certain pockets of the United States. I won't get into that, okay? But a 1-unit change means absolutely nothing, okay? So we have to handle the discrete levels of this kind of categorical predictor variable carefully when we're specifying the regression model, okay? So in choosing one of those reference categories, some people do that to aid a research objective or a set of planned comparisons, okay? So you might want to compare black and other individuals to white as part of your research question. Or some people simply choose the most prevalent of the groups to serve as the reference category. And they're saying, how do the smaller size groups compare to that largest, maybe majority group in terms of means on the outcome variable of interest, okay? But those are the two main ways that people choose a reference category. It's really up to you, given your research objective and the subject matter knowledge that you have. Okay, so there are other variables like this. We talked about race, ethnicity. It could be region, of the country, or region of the United States, or something like that. Or it could even be region of the county in the US. Could be different medical conditions or physical conditions, like do you have cataracts in your eyes? And it could be coded 1, 2, right? Now, this is another careful thing about just tossing variables into a regression model. Suppose that you had all these different kind of physical condition variables like cataract in the NHANES, and they're coded like you see here, 1 and 2, right? That might be okay for just adding that variable as a predictor to the regression model without creating an indicator, because a 1-unit change is meaningful, yes or no in this particular case. But what term in the model is going to be affected by just adding a variable like cataract, throwing it in there as a predictor? Based on the discussion that we just had, which parameter in the model is going to be adversely affected and is going to become meaningless by just tossing cataract into the regression model? Why can't I just toss cataract as a predictor into the model and be done with it? What's the implication of doing that? What parameter did we just talk about that's affected by how other predictors are coded? The intercept, right? So how would I interpret the intercept if cataract is coded 1 and 2? What does it mean for cataract to be 0? Nothing. I've made the intercept completely meaningless. Not because of a centering problem, just because of the way that this particular variable is coded numerically. That's it. So it's better to convert this or recode it to a 1-0 format where now 0 is meaningful. Maybe it means you don't have cataracts, or maybe it means you do have cataracts, depending on how you want to code it. Okay. Now, suppose I'm working in a survey data set where they were coding 1 was yes and 5 was no. Then I'm screwing everything up, right? If I just throw that variable into a regression model as is, a 1-unit change is no longer meaningful, and the intercept is no longer meaningful. So even though that variable only has 2 categories and I'm including it as a predictor, I can't interpret the slope and I can't interpret the intercept. Okay? This is why we have to think very carefully about how to deal with categorical variables. Again, in that situation, I would recode that 1-5 variable where 1 maybe stays a 1 and a 5 becomes a 0. Now the 0 value is meaningful. Now I can talk about a 1-unit change. Okay? So just be careful. Okay? It's almost a matter of common sense in these cases. All right, so carrying out this indicator variable method, let's look at an example where we have, again, that race variable that has 3 numeric categories.
Sorry, just got a question for clarification.
Yeah, go ahead, Nadia.
So for the binary variable, it's always better to recode it to 0 and 1. But for variable that has multi-levels, more than 2, is just leave it as is.
No, even for like I'm showing here with race, if you have 1, 2, 3, or it's 1, 2, 3, 4, 5, create dummy variables for all but one of those categories, which is the reference category. Yep. If you had a 5 category like self-rated health, for example, 1, 2, 3, 4, 5, and you just threw that into a regression model as a predictor, you're breaking the intercept, right? Because there is no value of 0. Right? You have to either, go ahead.
No. I'm just trying to understand. So basically, whatever it is, recoded to make sure there is one level that is coded as 0.
Yeah, there has to be a meaningful value of 0 on that particular variable, or if it's categorical, you'd recode it into a series of dummy variables.
Thank you.
Yep. Just be very careful. Make sure your intercept is always meaningful in these cases. Okay, so the more general kind of dummy variable coding technique, okay, we select one of those categories to be a reference category. Gave you a couple different ways you might go about doing that. So suppose in this case, we selected white to be the reference category, okay, using one of those 2 reasons. We create these 2 dummy variables, not 3, 2 dummy variables, because 1 variable is left out as the reference category. We create these 2 dummy variables for the non-reference categories of race. Okay, so x1 is going to be equal to 1 if race is 2 and 0 otherwise. x2 is going to be equal to 1 if race is 3 and 0 otherwise. So these are just indicator variables for those non-reference categories of race. Then we include each of those 2 dummy variables in the model as predictors. Okay, so now with this particular model, we specified 3 parameters that need to be estimated: the intercept beta 0, and then beta 1 and beta 2. So we're not just including race as a single predictor by itself, we're including 2 dummy variables for race as predictors in the model. So if we want to test the overall relationship of race with the dependent variable, we have to find a way of testing beta 1 and beta 2 simultaneously. We're going to talk about how to do that. Okay, so we have these two in the model. Now, how do we go about interpreting them? Well, again, go back to the actual equation itself. Go back to the regression functions. So the mean of y for a black respondent would then be beta 0 plus beta 1. Okay, because x1 would be equal to 1, right? The mean of y for an other respondent would be beta 0 plus beta 2, because now x2 would be equal to 1. And then the mean for white respondents would simply be beta 0, because both dummy variables are equal to 0. That's the reference category. So the intercept is giving us the mean for the reference category of the categorical predictor in this case. And then beta 1 and beta 2 represent changes in the mean. Okay? That's what we would call an effect in this context. How is the mean changing for black relative to white? And how is the mean changing for other relative to white? That's what beta 1 and beta 2 are capturing. They're differences in the mean of the dependent variable. Okay? Okay, so I mentioned that, how we interpret beta 1. We could also look at the difference in the regression functions for black and other to see the overall change in the mean for black relative to other. Okay, this is yet another linear combination. And we talked about what to do with linear combinations, right? If we wanted to get a test of significance, because this is just subtracting two coefficients that we're estimating. If we want to get a test of significance, we could take the variance of this combination. Variance of beta 1 plus variance of beta 2 minus twice the covariance of beta 1 and beta 2, and get a test of significance for that difference. Or what's an even simpler way to test the difference in the means between black and other using this approach? Here, white's the reference category, so I got to do all this additional work and get variances and covariances and yada, yada, yada to test this difference in coefficients. What's an even simpler way? I'm lazy. I want to compare black to other and test that difference for significance. What's an even simpler way? Well, that's one way, but that's still assuming that white is the reference category, right? If I want to compare black to other, how could I do that without doing any of this extra work? Say again? Well, that's what we're doing here. But to do this, I still need to get those variances and covariances and do the hand calculation. Who says I have to have white as the reference category?
Could you?
Right? If I want to compare black and other, just set other to the reference category. I'm going to get a coefficient for black. Just do that comparison, right? So you can do this kind of multiple testing just by flipping the reference category repeatedly. Sarah, did you have a question?
No, I was going to answer and, yeah. Sorry, I was
Okay.
going to answer and see if a test for significance of all of B1 and B2 both being 0.
Yeah, no, that's not giving us this. If we want a direct comparison of the means between black and other, we could just set one of them to be the reference category. Okay, so that's a way we can get these kinds of pairwise comparisons, but we'll talk about other ways as well. Okay, now how are categorical variables handled in the different software that we're talking about? And again, this is where we just have to be careful in the way that we're specifying a model. So in Stata, we're going to talk about using the SBY regress command. Okay, that's the command that we're going to use in Stata to fit linear regression models to continuous dependent variables. In your list of predictors in Stata, you indicate which of the variables are categorical by putting I dot in front of that particular predictor in your list. Okay. And so again, if you had like a 1,5 variable or a 1,2,3 variable or something like that, if you put I dot in front of that variable, Stata will create dummy variables for you for all but the lowest valued category of that variable. It sets the lowest valued category as the reference category by default. Very cool thing you can do in Stata is specify the reference category on the fly when you're listing a series of predictors. So instead of just saying I dot, which will set the lowest value category of the reference, you would say IB and then the number of the reference category that you want. Okay, so if I want category 3 to be the reference category, I would say IB3 dot, and then the name of that categorical variable. That will set that reference category on the fly just for the purpose of fitting that model. The key thing to do in Stata, don't just type cat var by itself for a categorical predictor, because Stata is just going to interpret it like any other numeric predictor and look at that relationship as if it was a continuous predictor with meaningful changes in values. Okay? Definitely want to avoid that. So we're going to repeatedly look at that kind of syntax in upcoming examples, just to make sure we get that down. Okay? Now in R, we're going to be using the SVY GLM function. This particular function in the survey package lets us fit a variety of different models, not just linear regression, but it defaults to linear regression if you don't specify some other distribution. Okay? And again, we input an existing design object and use a similar model specification like we've seen in other regression functions, but categorical predictors have to be specified as factor variables using the syntax that we've talked about. And R will do the same thing. If one of the predictors is a factor variable, it'll set the lowest alphanumeric value of that predictor to be the reference category. We'll talk about in factor how you can change that on the fly as well when we look at some R examples. But same thing as in Stata. If you have a numeric categorical variable, don't just enter it into the regression model. Make sure it's wrapped in the factor function, or that you define that variable to be a factor when you're setting up your data frame object. Okay? Just make sure you're not misunderstanding the relationship of that categorical predictor. So we'll come back to this when we get to examples. Okay, questions about dummy variables or categorical variable coding. Any questions about that? Very good there. So you can either create the dummy variables yourself, okay, which is usually good practice, or have the software create the relevant dummies and appropriate terms for you. We're going to keep talking about the syntax that you can use to do that. All right, so what about estimating these models? So in the case of simple linear regression, we've specified the model, we've selected our predictors, we've centered our variables, we've created the right indicator variables, and we're ready to actually get down to fitting the model to the data and estimating these parameters. So by far, the most popular method of fitting simple linear regression models is this method of least squares, or ordinary least squares, or OLS, as it's often abbreviated. So the idea here is that you estimate all those regression parameters by finding the values of those parameters that minimize this residual sum of squares that you see here. Why is it called a residual sum of squares? Because you're summing over everybody in the sample the residual, which is y minus the regression function. That's just solving for the residual squared. Okay? So in a survey context, this is just a total. It's a sum of squared residuals, but it's just another total. Okay, so that's going to become relevant as well on Wednesday. Okay? So we find the values of beta that make this sum the smallest. It turns out with OLS, you can actually write down an equation to solve for the values of beta that minimize those residual sum of squares. So there's a closed form solution. Very easy to compute the OLS solution in this particular case. And given an estimate of the betas, we can then compute an estimate of sigma squared, which remember is the variance of the residuals, that conditional variance of the residuals. We just take that estimated sum of squared residuals and divide by the sample size minus the number of parameters being estimated. Okay? That's going to give us an estimate of that residual variance. So we can get the estimates of the parameters that define a simple linear regression model pretty simply using this method of ordinary least squares. Okay? Now, there are many nice properties of this OLS estimate as well. It's very simple analytically. Like I said, there's a closed form solution. It's a linear function of the response value, so very easy computationally. It's also unbiased. So the expected value of that OLS estimate, given the values on the predictors, is equal to the true population relationship between X and Y. It also has the lowest variability among all other unbiased estimates. So it's not the only unbiased estimate, but it's the unbiased estimate with the lowest variability among all these other possibilities. And that makes it the blue, the best linear unbiased estimate, okay, of all these alternative choices. If we assume that the errors are normally distributed, the ordinary least squares estimates are equal to the maximum likelihood estimates. So there's kind of consistency in that regard if we're using maximum likelihood. Furthermore, under those normal errors, the sampling distribution of the regression coefficients follows a t-distribution. So we can use this relationship to test hypotheses about the individual parameters. So if, for example, a null hypothesis was that a given regression parameter was equal to 0, we simply divide the estimate itself by its standard error, and we can refer that ratio to a t-distribution. Okay, so that's a nice result that allows us to do quick and easy hypothesis testing. However, the OLS estimate is extremely sensitive to outliers in the data, highly unusual points, influential points that could affect the fit of the model in one way or another, and also heteroscedastic variances. There's that really long, ugly word. It just basically means variances that are not equal as a function of the predictors. Okay? So any of those key assumptions that are violated, or if we have outliers or unusual points in our data set, the OLS estimate can be extremely sensitive. And that's why model diagnostics are so important. Yep, George?
So this quick method is not, it's not when you are dealing with income. Let's say you are doing calculating.
I mean, it works, but it can be heavily affected by those extremely unusual values. So we have to think about how to deal with those unusual values, deal with those outliers. Should we leave them out? Should we modify the distribution that we're using for the dependent variable? Should we transform the dependent variable? That helps sometimes. We have to figure out how to deal with that. But you're right, it can be heavily affected by something like income. Right?
So we the same method of like distance or standardized residuals.
Yeah, stuff like that. That's what we're going to be talking about. Yep. To try to understand what the unusual points are, right? So that's why diagnostics are so important. If you never look at the data and you just go ahead and fit your models because it's easy and you get the output really quickly, you can really make some big mistakes about the model that's being specified, and your inferences can be affected accordingly. So diagnostics are just very, very important. Okay, another very common thing that's done in ordinary least squares is comparing two models. This is the idea of looking at change in R squared, or testing whether additional blocks of predictors are adding a significant amount to a given model. This is a very common test in the OLS context. Sometimes people call this hierarchical regression, where you're adding blocks of predictors to a given model and testing whether an additional block is making a meaningful contribution to a given model. So generally, if you have a set of all predictors X that can be divided into P1 and P2, different subsets of predictors, and you want to compare a full model that includes all the predictors of interest to a reduced model that only includes set 1, you can use this test statistic here, this F statistic. And notice what that means for the null hypothesis. Okay, the null hypothesis is that all the regression parameters for the predictors in that second set, X2 tilde, are equal to 0. So when you're testing whether a block of predictors is important and making a meaningful contribution, you're essentially testing the null hypothesis that all the coefficients of those predictors are equal to 0. It's just important to keep that in mind. Okay? So to do this overall test, given the sum of squared errors for the reduced and the full model, and then the number of parameters in each and the sample size, you can calculate this F statistic as you see here. And assuming that those residuals are normally distributed, okay, that test statistic follows an F distribution with the degrees of freedom that you see here under the null hypothesis. So we can then compute that test statistic to test that null hypothesis and see whether we would reject it and conclude that there is evidence that those additional predictors are in fact improving the fit of the model when we add them. Now, if we fail to reject that null hypothesis, we could certainly go with the simpler model. Okay, just go with the first set of predictors and be done with it. Okay? But again, all of this is in this OLS context under the assumptions that we talked about earlier. Okay, this F test holds under the assumptions that we talked about earlier, using ordinary least squares. Okay, so it's another pretty popular test. People using linear regression to make predictions are also interested in generating confidence intervals for predictions. Okay, so reflecting uncertainty if you're trying to make a prediction about the future. So there's a couple different ways you could go about doing this. One is to predict the mean of all the people who will have a common set of values on the predictor variables in the future. Okay. And that first approach to making a prediction in the future based on the regression function here, we can write down the variance of the predicted values based on that regression function. You see the basic formula for it there, which just ends up being a function of the covariance matrix for the estimated regression coefficients. Then we can write down a confidence interval for that predicted mean as the regression function plus or minus a critical t-value times the square root of that variance. Same way we've been forming confidence intervals before. Now, the important thing to recognize here is that that confidence interval for a mean does not take into account the uncertainty associated with individual predicted values. It's just looking at the variability of the mean itself, okay, as a function of the regression function. If you want to make a prediction for an individual element in the future, not a mean of all the elements that have the same values on the predictors, but an individual case. You're trying to make a prediction for an individual case. The variability of that prediction has to also incorporate the variability of the residuals. Okay, so these so-called prediction intervals are going to be wider for individual cases when you're making these predictions, because you're also incorporating the uncertainty in those residuals associated with making individual predictions, not looking at the overall mean. So the prediction interval looks very much the same, but under the root, you see that you add the variance of the residuals. And that's what makes those confidence intervals wider when you're talking about making predictions for particular individuals, as opposed to just looking at the mean for all the individuals that might have that value. Okay, so just something to keep in mind there. The key point about this slide is, again, when we talk about that variance covariance matrix of the estimated regression coefficients, here we're making assumptions about independent and identically distributed data, okay, like we would under simple random sampling. That variance covariance matrix is going to change when we deal with complex samples, okay, and that's what we'll be talking about on Wednesday. So when we form these confidence or prediction intervals for complex samples, we also have to reflect design effects. Okay, and that's what we're going to be talking about Wednesday. Okay, so that's another very common technique. Now, diagnostics and model fit. So you've estimated the parameters. Okay, you're able to calculate the variances, covariances under OLS assumptions. Okay. There's a number of different diagnostic plots that you can look at to check those assumptions. Okay. Key is checking whether the residuals follow a normal distribution. That's one of the fundamental assumptions that essentially activates all of these tests of significance that we were just talking about. You can use simple diagnostic plots to look at this idea of normality. So looking at quantile plots or QQ plots, histograms of the residuals. You can save the residuals in your data set and then plot them. Okay. And you can look at different types of residuals like studentized residuals or standardized residuals and look at plots of those. Okay. You can also use more formal tests. So you're not just relying on the eye test to look at the assumption of normality. You can test whether a given set of residuals is consistent with a normal distribution. So this is one example is the Kolmogorov-Smirnov test. This is one test that you can use to see if a given continuous variable is consistent with a normal distribution. The drawback of these more formal tests is that they're very powerful against the null hypothesis. So all it takes is a couple slight deviations from normality to give you a significant result. Okay? So usually it's a good idea to blend formal testing with informal testing to establish that there's evidence of normality. And most regression models are going to be, or linear regression models are going to be fairly robust to minor violations of normality. It's not going to have a huge effect on your inferences. Okay? So looking at normality of residual is a big diagnostic task. Looking at heterogeneity of variance, something else that can be done informally. Okay, remember, we're assuming that there's constant residual variance as a function of the predictors. So for this, you can also look at diagnostic plots and see, for example, if the spread, the variability in the residuals is the same as a function of different values on the predictor variables, or as a function of different fitted values. That's a very useful chart to look at. And there are also formal tests like the Levine's test to test for constant variance across different groups of cases. So that too needs to be assessed though. The idea that we have the possibility of heterogeneity of variance, okay? And outliers. I mentioned how OLS estimates are extremely sensitive to outliers, okay? These will often come up if you look carefully at residual plots, okay? Cases that are just way outside the distribution of the rest of the data, that may have a big effect on the fit of that overall model, okay? So getting into the habit of looking at residual plots, very, very important for linear regression. Influence statistics, so looking at studentized residuals, it's a way to scale those residuals given the standard deviation of those residuals. Hat statistics, which are measures of the leverage of a particular point on the overall fit of the model. Measures of influence like Cook's D statistic, okay, that I believe Newman was bringing up earlier. And there are many different textbooks of regression. You probably all had different textbooks when you were learning about linear regression, but there are many different textbooks that go into the importance of model diagnostics in detail. This Nieder et al. Is just one example, but there's many different good books out there that all emphasize the importance of looking at these diagnostics. So we're going to get into the habit of doing that as we go through different examples and trying to compute these. Now, again, all of this in a simple random sampling OLS context. For every single approach that we're listing here, we need to think about how that diagnostic approach changes when we're dealing with data from complex samples, okay? And what we're going to learn on Wednesday is that there's an entire package in R dedicated just to model diagnostics for linear regression in complex samples. That's how big the problem is, okay? All of these different steps, influence measures, hat statistics, residual plots, checking for things like multiclinearity between predictors, all of that, okay, requires adapting for the complex sample design features, okay? We're going to see how that works on Wednesday. These are all common tests in the simple random sample setting. We need to think about how this changes. So we'll talk about that on Wednesday, okay? So residual plots, very, very important. We can take the residuals from the fitted model, which again are just the difference between the observed value of y and what's predicted based on the regression function, once we've estimated those regression parameters, and then plot those residuals. Check what their distribution looks like, plot them against fitted values based on the model, plot them against predictors, and see if some of these assumptions make sense. So most of these diagnostic procedures involve inspecting plots of the realized residuals based on the fitted models, okay? So if you were to plot the residuals against the values of the predictors, that can indicate evidence of a nonlinear relationship that you missed in terms of fitting the overall data. So for example, if you had a relationship in the data that looked like this, where you have a predictor X and a dependent variable Y, and the relationship basically looked like this. Oops. That's 1.0. So it looks like an arch. And clearly there's a curvilinear relationship, right? Quadratic relationship between X and Y, but you naively did not look at the data. You did not look at a scatter plot or anything like that. And you just fit a simple linear regression model. The fit of that straight line is going to look something like this. That's going to be the ordinary least squares estimate of that regression relationship. That's the relationship that minimizes the residual sum of squares. Right? But if you then are smart enough to look at the diagnostics and you plot the realized residuals based on that model against the values on the predictor, guess what that plot's going to look like? The exact same thing. Why? Because I missed low here. I missed high up here, all throughout here, and I missed low again. The residual plot's going to have the exact same appearance. So if you miss a nonlinear relationship, that plot of the residuals against the continuous predictor is also going to be nonlinear. Okay? So that's a very quick and easy diagnostic plot that will reveal the fact that you may have misspecified your model and failed to capture the true nature of that relationship. Okay? Very easy to do, really no reason not to do it. Again, when you're being careful about the diagnostics here. Now, a plot of the residuals against the predictors can also present evidence of non-constant variance. So maybe for certain values of the predictor, the spread is really large in the residuals, but then for other values of the predictor, the spread is really small. That can say that the residual variance is a function of the values on that predictor. And there are ways for dealing with that problem as well. You can plot a histogram of the residuals. Just look at the raw distribution of the residuals, see if it's consistent with the normal distribution. The quantile plot, also very useful. So this plots the quantiles estimated from your realized residuals against those that you would expect based on a theoretical normal distribution with the same mean and variance. Okay. And do you see a straight line in that plot, which is what would be consistent with normality, or do you see a big deviation from a straight line, a big curve in that kind of QQ plot? That's another very useful tool for seeing whether or not you have evidence of normality in the residuals. And again, why is all this important? Because it activates those significance tests. All of those significance tests, for them to be valid, they rely on normally distributed errors. That's why this is important. Okay, so residual plots, very, very useful. And on Wednesday, I'm going to show you a very cool system that a professor at North Carolina State has developed to force his students to look at residual plots. He simulates data sets where if you are careful about fitting that regression model looking at residual plots, you get a work of art. He's come up with an algorithm where if the students do the right thing after fitting a regression model and they look at residual diagnostics, he's back transformed the data points from a literal work of art in the scatter plot to a data set. And when you create those residuals, you'll see that work of art. Okay, awesome. I'll show you guys that on Wednesday. Okay? But I just can't emphasize enough how important it is to get into this habit of checking residual plots. Okay, so let's look at an example. And again, all we're talking about today is simple linear regression, assuming we have simple random samples. Okay, ordinary least squares, all the assumptions that we talked about earlier. Let's just see how to do this in Stata and R. Okay? So what this is looking at is using the NHANES data, okay, and looking at a simple linear regression model where we're looking at the relationship of systolic blood pressure as a dependent variable, as the Y, with BMI as a predictor. So just simple linear regression to start with. So I'm opening up the NHANES data, and then I'm computing this so-called body mass index as a function of a person's weight in kilograms and height in centimeters. Okay. And then I'm only focusing on individuals who are age 18 and above, okay? And I'm physically deleting all those individuals from the data set, okay? So as some of you are hopefully noting, I'm doing everything wrong, right? Sadly, this is what the majority of the people do with the NHANES data. They fit models using the techniques that they know and love, and they get rid of the cases they don't care about, okay? So this entire set of code is naive. But it's important to recognize this is what a lot of people do with these data sets. And hopefully everybody now is gaining an understanding of what can go wrong when doing this, okay? But let's assume that the NHANES is a simple random sample and we're just going to use ordinary least squares on the subset that we care about. So I start with a scatter plot of systolic blood pressure by BMI. So in this data scatter command, the first variable is really the y-axis variable. Second variable is the x-axis variable. Okay, when you're making a scatter plot, and again, I'm restricting that to people who are age 18 and above. Okay, so I start with that scatter plot. Then I fit my regression model, where again, simple linear regression. In Stata's regress command, the dependent variable comes first. Okay, so that's BP syst on this line here, and then the predictor variables are listed after the dependent variable. Okay, and Stata's regression commands all work in the same way. So the dependent variable is always coming first, followed by the different predictors. All right. And then again, I'm being conditional, physically deleting the cases I don't care about, okay, for purposes of this analysis. Now, after you fit the regression model, right? We talked about lincom being a post-estimation command. We talked about the estat commands like estat effects. Another example of a post-estimation command that you can quickly use in Stata is predict. So after you fit a regression model in Stata, I can say predict, then type an arbitrary variable name. In this case, I'm calling it residual, comma, and then resid. That's the built-in option. That will save the residuals from that fitted model in a new variable in the data set called residual. And then I can do whatever I want with that residual variable. I can plot it, I can analyze it, but it's there. I can at least work with those realized residuals. Okay? So resid is one option in the predict command that will specifically save the residuals from that fitted regression model in your data set, so you can do whatever you want with them. Okay, so that's an important command. We'll come back to that with complex samples on Wednesday. Okay, so given those residuals, I can then produce a series of diagnostic plots, as I was saying earlier, for the model that we looked at here. So that scatter, that first scatter command plots the residuals on the y-axis against BMI on the x-axis. So residuals against predictor. See if we have a nonlinear relationship. See if there's evidence of non-constant variance, okay, and so forth. And notice how for each of these plots, I'm using the option name. Okay, this is something else cool you can do in Stata. Every time you make a plot like this, you can assign a name to it in memory, and then you can come back and combine all of those named plots into a single figure. Okay, so this is a very cool feature of the way Stata works here. All right, I'm also making a histogram of those saved residuals. I'm adding a normal density curve to that histogram, and then I'm naming that to be hist residual. Okay, hint, hint for the homework. Okay, there's a reason I included that. All right, then I'm using QQ plot. Okay, so I'm using Q norm, that's a normal QQ plot of that residual variable, giving that a different name. So I can refer back to that plot. Okay. Then the cool thing you can do, even when you've made a series of one-off plots, is use this graph combine command to put all of those plots together into one figure. Here I'm using the option rows 2 just to make a 2x2 matrix plot of these diagnostics. So then I can look at all of these diagnostic plots in one figure within Stata. Okay, make a decision about some of these different assumptions. Okay. Is everybody with me so far on this? Okay, again, just SRS, simple linear regression. Let's see what we get. Okay, so this is the Stata output that you see. Okay, so first you get your kind of analysis of variance table, right? Your sum of squares for the model, your sum of squares for the residuals, the total sum of squares, your degrees of freedom, right? Big data set, 12,000 cases, not any kind of adjustment for the complex sample design. Okay. R squared is about 0.1289. So R squared says what proportion of the variance in the dependent variable is explained by the predictor. So actually, given that this is just one predictor, BMI is explaining a big chunk of the variability, not all the variability, but a big chunk of it in systolic blood pressure, about 13%. Okay. And then you see the square root of the mean squared error. That's like your residual standard deviation. Okay, so that's like the square root of sigma squared that's being reported there. So that's your estimate of sigma squared. Then you see the ordinary least squares estimates of the coefficients for BMI, and Stata calls the intercept cons. So that term that's called underscore cons, that's the estimate of the intercept, okay, for that particular model here. All right, then we get that critical T value, okay, which shows pretty clearly that there's a strong relationship of BMI. I mean, that T value is 43, right? So we pretty much reject that null hypothesis at any level of significance and conclude that as BMI increases, so does a person's systolic blood pressure. The question is that happening in a linear fashion? And are there any other predictors that we should be accounting for in a model for systolic blood pressure? Almost certain, right? This is just capturing the simple two variable relationship that you see here. Okay, so if we look at these residual plots, first of all, we have systolic blood pressure against BMI. That upper left plot just kind of looks like a cloud. there's some evidence of a positive relationship, but clearly not everybody lies on that straight line. Okay, there's plenty of people with high BMI who have low systolic blood pressure. So there's some evidence of a positive linear relationship, but not strong. Okay. Then if we look at the residuals against BMI, what's something somebody sees in this residual versus BMI plot as it relates to our assumptions that we were making? What do people see here? What's that? Right, non-constant variance. Look at the spread here versus the spread over here. Right? It looks like the variance of the residuals is changing as a function of the values on the predictor variable. So that's one issue, right? Also seem to be some rather unusual points. Okay? Cases that seem to have extreme values on these residuals. And these are just the raw residuals. So these have not been scaled or studentized or anything like that. But it seems like there are definitely some unusual points here. Not surprising maybe, because we're just considering one predictor. Clearly, there are many other variables that might influence a person's systolic blood pressure. Okay, but we're just getting started. Okay? Then you see that histogram of the residuals with the overlaid normal density plot for the mean and standard deviation of that distribution. And looks like we're pretty far off normality, right? If we had a normal distribution of residuals, that histogram would lie entirely within that overlaid normal density. Okay? As you can see, it falls pretty far outside of it. So we have some initial concerns about that assumption of normality. And then if you look at that quantile plot, okay, we want that kind of plot to be a straight line, showing the actual residuals against their theoretical quantiles from the same distribution, not even close. Okay, so looking at this plot, we're worried a little bit about residuals, and we're worried definitely about the assumption of normality for those residuals moving forward. But we're not overly surprised because, again, we're just considering one predictor variable so far. And there could certainly be others that fix up some of these problems if we try to explain more of the variance in the outcome. Okay, so thinking about interpretation a little bit with what we saw here. So in this example, again, we're looking at the relationship between systolic blood pressure and BMI. Okay, the unadjusted estimate of the regression coefficient was about 1.7 with a standard error of 0.04. So clearly a significant relationship here, a significant positive relationship. We know that the standard deviation of BMI was about 5. So given all this information, another thing that people do to help with interpretation, we could just say that as BMI goes up by 1 unit, you would expect a person's systolic blood pressure, their mean systolic blood pressure, to go up by 1.7 units. Okay? That's that positive relationship. That's that standard interpretation of that estimated coefficient. But some people talk about how an expected value on the dependent variable changes as the predictor changes by 1 standard deviation. That's another way to talk about these results. So as the predictor goes up by 1 standard deviation, what happens to the mean of the dependent variable? Well, given that we know the standard deviation of BMI, we can just multiply that regression coefficient by that standard deviation. That gives us the expected change in mean systolic blood pressure with an increase of that amount. Okay, that's just plugging that value into the regression function. So it goes up by about 8.5 on average. But the question is, how do we get the standard error of that increase? If we want to make inference about that increase, we can just take that as the standard deviation of BMI and multiply by the standard error of the estimated coefficient. Okay? That will give us the standard error of that increase in the mean of the dependent variable, just using the regression function and using the standard error of the estimated coefficient. Okay? And that's about 0.1969. Okay? So not only could we say how much is the expected change with a 1 standard deviation increase, we can also attach a standard error to that using this kind of approach. So that's just another way to interpret that estimated coefficient. Now, clearly, again, there's other variables that we could add to this particular model. Okay, so one example is adding race ethnicity. We could also add poverty index. Okay, we could add age. We could add gender. This is just a few of the variables that we might add to adjust for when looking at this relationship of BMI with systolic blood pressure. So note carefully what I'm doing with the syntax here at the top. I'm creating dummy variables for levels of race ethnicity in the NHANES, but I'm also being cognizant of the missing data. Okay? So I'm starting with a variable equal to 0 for everybody. This is black indicator. I'm replacing black with a 1 if race is equal to 2. But then I'm replacing black with a missing value if the original race variable has a missing value. So that way I'm not just arbitrarily recoding missing data into a 0 category. I'm still explicitly accounting for that when I form my dummy variables. Okay? There are other ways to create dummies in Stata, to be sure. This is a careful way so that you're carefully handling missing data. And you're not just arbitrarily coding missing data into a 0. Right? So remember, that's critical for forming these dummy variables as well. And then I do the same thing for other. Okay, so I create a dummy variable for other. So what I'm showing you then in the subsequent regress command is now I'm adjusting for the values of all these other covariates. So I have regress, and then systolic blood pressure is the dependent variable, but then I list multiple predictors, not just one. So I have age, I have IB2 gender. Okay? That's saying I want 2 to be the reference category of gender in this particular model. Okay? Otherwise, Stata would use 1 as a reference category. Then I include the dummy variables that I made from scratch. So see, I could go either way. I could have said IB1.race, and I would have had the exact same result as I have here, where I made the dummy variables manually. So I could go about it either way. I'm just showing you both possible ways of creating dummy variables in this particular case. So I can use IB reference category dot variable, or I can create the dummy variables myself. You'll get the same results either way. You just have to be careful about missing data if you create the dummy variables yourself. Then I also adjust for poverty index, and I have BMI as my main predictor. Okay. I fit that model use. Oh, that's your question.
Yeah, if you use YB, if you respect that the incident.
Yes, yes. So using IB would handle the missing data correctly. That's right.
Okay.
So it'll leave those cases out of the analysis either way. That will do it automatically. Creating dummy variables manually yourself, you have to be careful of that. Yeah, it's a good question. So IB doing it on the fly will handle the missing data correctly. Okay, so I fit that model. Again, save my residuals, but notice I saved the residuals in a new variable, residual 2. Okay, so I'm not creating the variable that already exists. Then all of my subsequent diagnostic plots are using residual 2. They're not using the original residual variable. So I just formed another new variable based on that second model. Okay, and that gives me my plots. I've included a link here for those of you using R, where you can walk through basically all the same steps, including diagnostic plots, using the LM function in the base R software to fit these linear regression models. So take a look at that web link, and it's a simple walkthrough, kind of like we're doing here with dummy variables and so forth. Okay, so here's the updated regression fit. Okay, so I see R squared is now 0.32. So adding these additional variables, I've got my R squared up to about 32%, just getting in the right direction, seems like. Okay, many of the predictors are significant with the exception of other. So if I look at this interpretation here, remember these estimated coefficients for categories of race are relative to the reference category. So if I look at that estimated coefficient of 0.67 for other, that's saying that the difference between other and white is not significant if I look at that critical T value. So I could probably combine other with white into one group and compare them collectively with black and simplify my model, okay, without losing too much in terms of the variance explained. Okay. Looking at my residual plots, okay, looking a little bit better. There's still some outliers, okay. The histogram looks a little bit better. It's now more contained within the overlaid density plot. QQ plot, though, still has some issues, okay. And like George was saying earlier about income, seems like we have these really extreme values on the tail end of systolic blood pressure that we still need to account for, that even these predictors aren't fully explaining. So we might need interactions. We might need to transform the dependent variable. There's additional steps we could take at this point. We're doing better with this model, but there's still work to be done. given that QQ plot. And this is the iterative process that you need to consider when fitting these models. We would really stop when we're happy with all these diagnostic plots, and we're happy with all of our estimated coefficients. We're better now, but we're not quite to the end, given these diagnostic plots, assuming again that this is a simple random sample. Okay? So another key thing to note, and then we'll stop here. The adjusted estimate of the BMI systolic blood pressure relationship is 1.25, okay, with a similar standard error. But what's interesting to note is that the adjusted estimate is about 12 standard errors below the unadjusted estimate, okay? Big difference. So when you adjust for all these other characteristics, that relationship is not nearly as strong as we initially thought it to be. So in this case, very important to adjust for the other covariates that are being considered in this model before we make inference about the relationship of BMI with this particular outcome. Why is this happening? Because the adjusted estimate gives us a sharper comparison and essentially equalizes people in terms of their age, their gender, their race, their poverty index, when we're estimating the relationship of BMI with systolic blood pressure. Now we're saying for somebody who's the same age, the same gender, the same race, and the same level of poverty index, if we compare different people in terms of their BMI, what's that relationship? And that gives us the adjusted estimate. Okay? And furthermore, we could simplify the model by dropping this other variable based on the t-test that we saw. Okay? Okay, so I think we'll stop there for today. I'll come back to a couple of comments about transformation to kick off the discussion on Wednesday. And then we'll get into what changes with simple linear regression when we're dealing with the features of complex sample designs, okay, and what we need to do with them. Okay, so questions, comments, either about the software here or interpretation or anything else we've been talking about today? Questions or comments at this point?
I have
Yes,
a
sir.
question, slide number 21.
21, yep. Okay.
Here we are going to make some diagnostics for randomized, for example, graph, something like that.
Right.
But depending on all the time, for example, it's maybe misleading because it's subjective from person to
Right.
another. So is there any, not for normality, for linearity, for example, is there any specific test, parametric test that can
Sure.
be used?
You can actually fit a model to the residuals because they've been saved in your data set, right? So you could fit a model to the residuals, say, like I was showing in that earlier slide, if you had evidence of a nonlinear relationship of age with the outcome, you could say, what's the relationship of age with the residuals? Treat the residuals like a dependent variable, and then fit a model that allows the relationship of age to be nonlinear, and see if there's evidence of a significant nonlinear relationship of age with the residuals. So as long as you have those residuals saved, treat them like a dependent variable.
Okay. So after that, if I didn't find any relationship
Yep.
as linear,
Yep.
so I have to make a transformation on axis, right?
Possibly, that's one solution. Yep.
Okay. What about if I make many transformations, even if Fox also,
Yep.
but doesn't work?
Yep.
What about
Then you have to think about, okay, do I need a different model altogether? Should I categorize values on the predictor, right? Should I turn that into like a grouped ordered variable or something like that? Then you need to think if there's no evidence that I can find this right kind of relationship, you might need to recode either the dependent variable or the predictor or both, or think of just a different potential model where simple linear regression may not be the best way to describe this particular data set. But at that point, it's probably going to involve recoding or transforming the variables in some way if you just can't find any good solution.
can I ask another question?
Sure.
Slide number 8.
Yep.
George asked here about after controlling the variable z.
Yep.
Okay. And you explained it by introducing categorical value. It's okay for me, but what about if he was a continuous variable in that case?
Same thing. Yep. So I just used the categorical variable just for simplicity because you can compare 1 to 0 very easily. But if z was continuous as well, you're saying I hold z at fixed at that value when I interpret the relationship of x. And then in the context of interactions, you're still talking about what happens as z increases by 1 unit. How does that relationship change as z goes up by 1 unit? So z does not have to be categorical. You could have an interaction you're using a continuous z as well.
And in this case, I make a control for z, but what about if controlling that, what about if we remove it from the model and just make a model without it?
If it has no relationship and it's not adding anything, you could certainly do that.
Slide number 7.
Yep.
Here, it's a very simple question because here we talk about sample linear regression. From my understanding, it's maybe you have only one predictive variable X.
In the simplest linear regression model, right? The linear regression model I'm talking about here, you could potentially have multiple predictors. That's just a terminology thing. So some people say simple linear regression is where you just have one predictor. Some people say simple linear regression is one predictor and no intercept. Here, I'm just saying the general specification of a multiple linear regression model, as it might be called, where you have multiple predictors, would look like this. So it's just semantics.
That was the question. Slide number 5.
Okay.
What about nonlinear model? Is it possibility to linearize the model by taking length, for example? Is it possible to do that?
No, you would never linearize a nonlinear model because usually there's scientific interest in the functional form that's been specified here. So there's specific scientific interest in estimating beta 2 because that describes some kind of physical relationship between variables. So you wouldn't linearize this just to turn it into a linear model. You would use estimation techniques that allow you to compute estimates of those parameters because you have reason to believe that that model best describes its relationships. Yep. Yeah. So that's okay. There's usually a reason to specify the model in that way. So. Yep. Thank you. Yep. Other
Sorry,
questions?
I got a question about the, I think the last slide about the diagnostic plots. So if we fit a model in the survey design, like survey regress, and I saw that we only did that assuming SRS. So how does that work out?
That's Wednesday. So yeah, now we're going to talk about all those adaptations for complex samples on Wednesday. We haven't talked anything about that yet.
Okay.
Okay.
So it's mentioned it's more serious, like
great question. In my experience, especially with these large data sets, it's usually the non-constant variance. Unless normality just looks absolutely terrible, right? You'll find that even if you've transformed or you've implemented some other fix for the lack of normality, you're still making the same inference with a large enough sample. It tends to be a bigger deal with small samples, but the non-constant variance tends to have more of an implication, especially for the standard errors of your estimates. And so what we're going to learn about on Wednesday is like using weights to deal with non-constant variance. That's one possible approach, but the role of weights is going to be taken over by survey weights. So we have a complication in how to deal with that. We're going to start off Wednesday talking about that. So, but yeah, it's usually, in my experience, that's usually the bigger deal. Okay, other questions? These are all great questions. Okay, definitely send me emails then. So again, I think there were a couple of cases this week where Yang Chao got emails, but I didn't, and Yang Chao's busy. So definitely CC both of us to any emails related to the assignment so that one or both of us can see them more quickly. If you have questions about homework or about the project. So, okay. Okay, thanks everybody. We will see you on Wednesday. All right, good morning, everyone. I think we're going to go ahead and get started here. So just a little bit about the agenda for today. We've finished grading homework number 3. So we're going to start by going over those solutions and some of the points that came up in that homework assignment. Then we're going to return to the lecture notes from yesterday and finish up our discussion of the basics of linear regression. And then the bulk of the time is going to be spent going over what changes in linear regression for complex sample survey data, and we'll look at some examples. Okay, so that's our agenda for today. I posted an announcement just as a reminder that the initial drafts of your final project are due on Friday. You do have until the end of the day on Friday, so it doesn't have to be turned in right at 9 o'clock when we're starting with the lab, but please do try to get the actual drafts in. Remember that is just the introduction and the data and methods. You do not need to show any results. You do not need to show any tables. That's not what you're being asked to do for this particular assignment. Just the introduction, just the data and methods. Okay, so make sure to go back to the project description, make sure you're clear about what's being handed in. As I mentioned in the announcement as well, take a look at those templates that are up on Canvas, get a sense of what we're looking for with those two sections. Okay, you don't have to do an extensive literature review for the introduction. Just a couple citations that motivate what it is that you want to look at would be perfectly fine. Okay, so it doesn't have to be very extensive, and this is just a draft. So I'm just going to make sure you're on the right track, give you some basic feedback about those two sections. And also, as I mentioned in the announcement, make sure that you do have a draft of your statistical analysis plan as a part of the method section. So that'll just outline for me what exactly it is that you're planning to do for the final project, more specifically in terms of the data analysis. Okay. So questions about that particular assignment? Any questions about what's due on Friday? Everybody clear on that? Yep, now?
So what are you gonna say about handling missing data?
If that's part of your methodology, that would be part of the statistical analysis plan. So the data and method section is everything that you're planning to do, just not showing the results. Yep.
But even though we haven't done that yet.
Yeah, you can say I'm planning to, do multiple imputation or whatever, but the details will be included at a later date or something like that. Yep. I just want to make sure I have a full idea of what you're doing for your data analysis and that it's consistent with what you've laid out in your introduction. That's what I'm primarily going to be looking for. Okay, other questions about what's due on Friday? Any other questions? Okay, good. All right, let's talk a little bit about homework number 3. For the most part, everybody did fine. There were just minor errors here and there. So one key thing that came up, and I'm showing you here, the solutions are now posted up on Canvas. So you'll see the solutions for homework number 3. One issue that did come up is when you're reporting that Rouse-Scott test. So I'm showing the output here for 6.1. Remember that these are the design degrees of freedom. Okay, that's what we have available for variance estimation purposes. But when we're reporting the F tests that comes from those Rouse-Scott adjustments and the additional adjustment to the chi-square statistic by dividing it by its degrees of freedom, we actually have 2 degrees of freedom values for that F statistic. Okay, so a common error that came up is that people were reporting an F statistic, but then just the 1 degrees of freedom value associated with the design. Anytime that you're reporting an F statistic, you need to make sure you're reporting both of those degrees of freedom values. Otherwise, that's going to confuse people who are reading that statistical output. Okay, an F quantity is always going to have 2 degrees of freedom values. Okay, so that's something that came up repeatedly here. So another issue that came up, just be clear about the variance estimation methods that you're using. So there were a couple of people who you were forming confidence intervals, but it wasn't clear based on what variance estimation method you were using, okay, to form those intervals. So whether you're using a replication method or you're using linearized methods, which again are the default, just make sure that you're clear about that as part of your solutions. Okay, but like I said, for the most part, there were just a couple minor errors here and there, and everybody seems like they did a pretty good job. This solution set will include both the Stata code and the R code for executing all these different problems. You can refer to that code and just see if there were minor errors that you made where you might have deviated from what we felt was the ideal approach in the solutions. Okay, but again, most everybody's doing very well in the homework, so that's looking good. All right, so take a look at those solutions. If you have any questions, just send a note, send an email to me and Young Chow, and we can get back to you and resolve anything that that might have come up. Okay. Okay, so those grades are going to be released soon. And again, the solutions are posted up on Canvas. All right. So turning back to our discussion from Monday, before we get back into our discussion and the example that we were talking about, any general questions about linear regression or regression modeling approaches that we discussed on Monday? Any questions before we jump back into the lecture notes here? Questions, comments? Okay, good. All right, so we talked about the importance of looking at diagnostic plots when fitting linear regression models, and the assumption that the residuals are normally distributed. One common remedial measure when you find evidence of non-normally distributed residuals, especially for financial variables, things like income and wealth and assets, where there's tends to be a skewed distribution for that continuous variable. One common remedial measure is to transform the dependent variable and then fit the regression model to that transformed dependent variable. You just have to be careful about the way that you transform the dependent variable, because it can mess with the nice interpretation of the parameters in that model. So we talked about the additive interpretation, right? A 1 unit change in a given predictor changes the expected value of the dependent variable by whatever the beta quantity is for that particular predictor. We talked about that interpretation on Monday. When we transform the dependent variable, that changes the way that we interpret those beta parameters. So here's one example of a very common transformation that's used in response to seeing diagnostic plots that don't look ideal in terms of distributional assumptions, especially when you see evidence of a skew in the residuals, is the natural base E log transformation of the dependent variable. So this shows what a simple linear regression model just with a single predictor would look like if we, instead of modeling the actual variable y, we modeled the natural log transformation of the variable y. So the key thing to note here is that the regression parameters really are now on a multiplicative scale, okay, when you take that natural log transformation, okay? So as a predictor variable increases by 1 unit, the key thing that changes with the natural log transformation is that the mean of the dependent variable is multiplied by a certain quantity now, not the actual regression coefficient, but the exponential of that regression coefficient when we use that natural log transformation, okay? So we can't just take the beta 1 coefficient and say that the dependent variable increases on average by this much. We have to exponentiate that coefficient and then say that the mean will be multiplied by the result of that calculation. Okay, that natural log transformation, again, changes the basic interpretation. It means that when we're using that natural log transformation for the actual modeling, we have to now talk about changes in a multiplicative sense rather than an additive sense. Okay, so there's kind of a two-step change in the way we interpret. We exponentiate the estimated coefficient, and then we would say that the mean would be multiplied by whatever that exponential value is as the predictor variable goes up by 1 unit. Okay, so that's still a relatively straightforward interpretation in this case, but there are many other kinds of transformations that you might consider. I think Isra mentioned the Box-Cox transformation on Monday. That's a family of transformations that we can consider to try to achieve the assumptions that we have about this model. There's many varieties of transformations. This is one that's commonly used and still has a relatively straightforward interpretation. We just have to be careful about how we're doing that. And we'll talk more about this kind of transformation in lab on Friday when we go through some examples of modeling a log transformed dependent variable. Okay, but just something to keep in mind given how common it is to model the natural log transformation of a continuous variable. Okay, another remedial solution when the diagnostic plots don't look good, and this will lead into our discussion today, is weighted least squares. Okay, so when you look at those residual plots, and you find evidence of non-constant variance or heteroscedasticity, okay, in the residuals, you could either transform the dependent variable or model the variability of the dependent variable directly. Okay, so there's different options you could consider. If you're trying to model the variance of the dependent variable via the residuals, you can use what's called weighted least squares, or WLS. So far, we've been talking about ordinary least squares, and weighted least squares traditionally is an approach that's used to accommodate non-constant variance in those error terms. Okay? The way that this works is you look at that residual sum of squares, and now each person's contribution to that residual sum of squares is inversely proportional to the residual variance for that particular individual. Okay, so the weight that's used in this residual sum of squares is inversely proportional to the residual variance for that case. So we allow for non-constant variance, but the weight that each individual gets in that residual sum of squares is a function of that error variance for that particular case. And that allows us to model that variance directly as part of the estimation. Okay, so here's an example of what that might look like. Suppose that the variance of the residuals appears to be a function of the predictor variable x1. Okay, and x1 tends to be a positive value, whatever the predictor might be measuring. So we can write that the variance of those errors is not equal to that constant, sigma squared, but it's equal to that constant multiplied by the value of that predictor variable. So as the predictor variable gets larger in value, the variability of the errors becomes larger as well. This is the idea of non-constant variance. And this can be common for certain types of predictors. In that situation, the weight that's used in the weighted residual sum of squares would be the inverse of that residual variance, which again is going to be a function of x. So what that means is that the weighted residual sum of squares just becomes a slightly more complicated expression. We still have a closed form solution for how to solve that, but it involves the weights of the individual cases here and allows that error variance to be a function of the predictor variable x. Okay? And you can use a variety of different weights depending on what you see about the residual variance in that case. Okay? The idea is that you're applying this differential weight. So for example, if a case has a larger value on x and they have larger error variance, that case would get less weight in the residual sum of squares. So the cases that have smaller error variance are going to get more weight in the residual sum of squares. And that's the way that we can accommodate that non-constant error variance. Okay. So again, traditionally, weighted least squares was developed as a method for accommodating those kinds of situations. And this is just one simple example of what those weights might look like. Okay. What we're going to see today is that in the context of analyzing complex sample survey data, the exact same machinery is used to accommodate the survey weights. Not weights that represent non-constant variance, but rather just weights that represent how many people in the population a given survey respondent represents. So survey weighted estimation of linear regression models is still going to use the weighted least squares machinery. It's just that the weight is playing a different role. And we're using it to estimate what the residual sum of squares would look like in the larger population, just like we've done with every other total. Okay, so we'll see that in a second here, but we're using the same technology, just a different type of weight for the purpose of accommodating those weights in estimation. Okay, so we're going to come back to that here in a second. Yep, Sarah, do you have a question?
I do. Looking at this slide. So if I'm just verifying I'm interpreting correctly. So WI is weight to individual I, and the WRSS is what we're minimizing, right? So we're now instead of so that's also going to minimize the sum of the squared errors, but now incorporates the XI in the denominator for the new adjustment for the weight, right? But we're still minimizing some of this factor in order to compute our BI estimates or BS. Okay, thank you.
Yep. Same idea as ordinary least squares. We just have a differential weight for different cases. And that's what we're going to leverage for today when we talk about accommodating weights when fitting linear regression models. Yep. Okay. Other questions about this idea here? So there are many different remedial measures for these kinds of violations, apparent violations of assumptions. We've just introduced a couple of them, but this should hopefully just be a reminder, a refresher of what you've learned about in previous courses about linear regression. The reason we bring this up is, again, because we're taking a common remedial measure for non-constant variance, and we're using that as a method to accommodate the final survey weights when fitting these regression models. Okay, that's one of the things that changes here. Okay.